G'day guys, Mr. Bennett here. I just want to go through a bit more of a summary of projectile motion. I'm going to do a question as well. So if we look at a projectile which is just launched horizontally, what's going to happen? It's going to fall to the ground with a parabolic path, right? You can sort of see the path following here. So we've got two images here. So this is the case where if you drop a ball, or if you launch it horizontally. Now, the interesting thing is, if you look at the blue dots along the top, is the distance is the same. So that means that our projectile here is travelling at constant horizontal velocity. And that's what we should expect with a projectile, because the horizontal acceleration is in fact zero. In the looking at the vertical component is, you notice the gap starts to increase. The reason why that happens is because the projectile is in fact accelerated due to gravity. Right? So the thing is, which is interesting, is the height, no matter if it's launched horizontally or if it's just dropped, it's going to be at the same height each time corresponding. Can you see that? Okay, so if we just go to the thing, you can see it lines up quite clearly to see that the actual height is independent of the actual the horizontal velocity. All right, so in terms of that, the motion is accelerated. It is accelerated due to gravity. The acceleration is constant and it's downwards. All right, we know that gravity acts at 9.881 meters per second. Generally, would say it's got the symbol G. The horizontal component of velocity is constant. Horizontal and vertical motions are independent of each other. They're the key things that you need to understand about projectile motion. So if we launch something from the ground, okay, what's going to happen? It's going to go to a maximum height, and then it's going to go back to the ground at the same position there and land. Now again, you can see by the constant spacing there that the horizontal velocity doesn't change. As the projectile goes up, it slows down. Okay, it's to a height here. We would say that the velocity vertically is actually zero at that place, and then it accelerates down due to gravity. So gravity is the thing that slows it and stops it from going upwards, and gravity is the thing that accelerates it, making it go to the ground and speeding up. Again, the motion is accelerated, acceleration is constant and downwards. Alright, so we know all those things still apply to this situation as well. Alright, and we know gravity is that. Now, we probably won't look at this until year 12, if those people do year 12, but this is an interesting concept, which is if you launch a particular projectile at say 15 degrees, right, it lands there. If you launch it at 75 degrees, it still lands at the same place. So these are called supplementary angles. The reason there is we've got a lot more of our motion provided as a vertical velocity there. Here we don't really have a very big time of flight. I'll just go back to that previous slide. We don't really have a lot of time of flight there, so therefore you'll find that it doesn't go so far. Again, if we look at an angle of 30 degrees, the supplementary angle will be 60 degrees. Okay. For a projectile launch from ground to ground, the best launch angle is 45 degrees. So that's what this slide talks about. Now, when you start looking at the velocity, you can break that into vertical and horizontal components. Okay, so here obviously the vertical component's bigger. There, the vertical component drops. We notice that the horizontal component is the same no matter where it is on the thing. At the top, it's only got horizontal component. So technically, at the top, the projectile is actually moving the slowest at that point there. Okay, as it comes down here, it picks up more vertical speed, so therefore the component of velocity increases. Alright, so that's that PowerPoint. Now, I want to go through a question with you that basically goes through the steps that you'll need to know. And I'll give you a copy of this sheet. And so this is basically everything that you would need to have to be able to do for projectile motion. So the first thing here is a cannon's fires a cannonball at 800 meters per second at an angle of 40 degrees above the ground. So here's my formulas to work out the horizontal and vertical components. That's what we need to do. So if we work in black, so if we working those things out, we've got our diagram which is drawn there. So we could say our V vertical is equal to V sine theta, so that's going to be 40. Sorry, it's not V, it's 800. So it's 800 sine 40. And then we know that our V horizontal is going to be equal to 800 cosine 40. Now, in most questions, you'll be asked to do that, but if you're not asked to do that, then what we'd expect you to do is to actually find that value anyway. So just make sure your calculator is in degrees and not radians. Yes, it is in degrees. So if we go 800 sine 40, then that will give us an answer. And we do 800 cosine 40, that will give us our answer as well. So it's 514.23 is the vertical component. Go back to there. So that's equal to 514.23. Now, units are metres per second, so you need to write those down. Another one is going to be 612.84. You have to round that up to 84. So that's 612.84 metres per second. So in a test or assignment, you get basically marked for doing each of those. The next thing that we have to do is to work out the actual time of flight. Right? So now, if we're looking at our projectile, cannon's fired above the ground, so we're assuming here it's going to go in a path where it goes and lands at the same height. Okay, so in this particular case, we're assuming our S vertical, the difference between where it starts and where it finishes is actually going to be 0 metres. Alright, so therefore, we're only going to use the vertical component of this formula to work out the time of flight. So we're going to say here, 0 is equal to, now initial vertical velocity is 514.23 times by t. Now gravity, we know, is minus 9.8. So a half of 9.8 is in fact 4.9, and we've got to do t squared. So if we bring out a common factor of t, then we're left with 514.23 take 4.9t. So therefore, t is going to be equal to 0, or it's going to be, if you do the algebra here, 514.23 divided by 4.9. So let's just do that. 514.23, divide that by 9.8. Sorry, not 9.8, 4.9. And that will give us an answer of 104.9 seconds. So let's go back to that. So that's our time of flight. So it's either t equals 0 or 104.9 seconds. So it's in the air for a fair while because, you know, literally cannonball, you know, will travel a fair distance, and we're going to work that out next. So we always use this formula here for working out time of flight, no matter what the scenario is. The only thing that will vary in this particular case will in fact be this value here and the vertical velocity. Alright, that's what's going to change in this thing here. That will always be minus 4.9. Alright, because we're doing, or unless we go to another planet. In this case, we know we're going to stay on Earth, and it's always going to be that value. Now, the next thing we've got to do is work out the range. Now, the range will be how long it's in the air for, times by how fast it's actually going horizontally. So if we work out our SH is equal to, and you always write the formula down, that's always part of the thing that we're doing. So our SH is going to be 614 what was that value again? I can't remember quite 612.84. So 612.84, and we're going to times that by the time of flight, which is 104.9. So if we go to our calculator and we just simply multiply that by 612.84 0.84, and that's going to give us an answer which is 64,314.4. So go back there, we can write that down, 64,314.4 metres, and so you might even say it's approximately equal to 64.3 kilometres. Alright, so that's how far the cannon's going to go. So it's obviously a fairly big gun we're looking at here. So that would be a question that you, most of the time you would do. Calculate the final vertical velocity when it hits the ground. Well, without actually doing any work, I know the final vertical velocity should be, in fact, its initial velocity, which is equal to 800. Okay, and it should be going down at 40 here. Should make this angle over here equal to 50 degrees. But let's do the calculation so we can actually work that out. The thing that doesn't change is the horizontal velocity. We know that's always going to be whatever it was at the start, and so we know that's going to be 612.84 metres per second. The thing that does change is the actual final velocity. So we have to do that first, find the final velocity. V vertical is equal to our V vertical initial plus a v times by t. So therefore we know initial vertical velocity was, I'll go back to my calculator, we'll go back to the sheet, it should tell me. So just scroll up. So initial vertical velocity was 514.23. So that's 514.23. And that's going to be take 9.8, because that's what gravity is, add negative 9.8 is like take 9.8 times by t, which is 104.9. So if we go to the calculator, so 514.23 take 9.8 times by 104.9. It's going to give us a value of negative 513.79. Alright, so negative 513.79 metres per second. Now, I would expect that to be negative because we are expecting this thing to be travelling downwards, and that's what the negative means. So the next thing that we would do to work out the velocity would be equal to the square root of the horizontal velocity squared plus the vertical velocity squared. So that's going to be 612.84 squared. Add, now you don't really need to worry about the sign there because it's a vector quantity, it's going to be squared anyway. 79 squared. Now if you do that in your calculator, you're going to get 800 metres per second. I know that's what's going to happen. And then obviously to work out the angle, right, so the angle that this thing's coming down at, that thing, generally what we do is we say that angle there, so it's below the horizontal. So theta is equal to the inverse tan of the opposite side over the adjacent side. So as this works out, theta is always the vertical component of velocity over the horizontal component of velocity. So in this particular case, inverse tan of, I'm just using some trigonometry, it's going to be 513.79 all over 612.84. Now if you do that, I know you're going to get an answer of 50 degrees. Right, so you can do that in your calculator. I won't do it on the calculator because of time in this particular thing. Find the maximum height of the projectile. So in other words, when this thing goes to maximum height, what we know here is the vertical component of velocity is 0 metres per second. In this case though, it should be half of the time of flight anyway. But let's just do it so we don't really, we can do this at any time. But so we're going to use this formula here to start with. So we're going to say our vertical velocity there is in fact equal to 0, but that's equal to 514.23 take 9.8 times t. Okay, because that's what our acceleration is. And so therefore, if we do that, our t should be equal to negative 514.23 divided by negative 9.8, and that should give us an answer of 50, it's 102, so it should be 50, well, sorry, it's 104, so it should be 52.45 seconds. Alright? Now, once we've got that time of flight, the next thing we need to do is work out how high it will go. So SV is going to be initial velocity, 514.23, times by that time, which is 52.45, take 4.9 times by that time, 52.45 squared. And that should give us our vertical displacement upwards. So let's go to our calculator, do that. So we've got 514.23 times my 52.45, take away 4.9 times by 52.45, and we have to square that, don't we? And we press equals, so that tells us 491.5. So that's equal to 13491.5, which is approximately equal to 13.5 kilometres. Okay, that's our approximate answer there. Alright, so we've now pretty well gone through a whole question. Now, in projectile motion, this is everything you could probably be asked to do. Alright, so there's an example for that. This will be enough for this video. I'm going to go through a couple other examples in some other videos to help you look at different scenarios that you might see.